Hello, in this video we'll be going over cryptography, its properties, different types of ciphers, that sort of thing. Cryptography is the science of hiding information, securely transmitting information, that sort of thing. And then we'll be going over some cryptanalysis techniques, the different tools and techniques you can use to break ciphers. So starting with the purpose of cryptography, cryptography is kind of defined by its purpose. Uh, it's really known for doing four things: confidentiality, providing that, providing a means to authenticate, and providing verification of data integrity, and finally non-repudiation. And we'll be going over how it does these four things later on. It's important to get the definitions right so we're all in the same terms here. Plain text, that's the input you're putting into the crypto system. So that's your message, it could be, or a file. Ciphertext is the result of encryption, so that's what you get after you encrypt your plain text. Encryption is uh, the act of concealing or manipulating the data to be unreadable. Decryption would be the opposite of that. And a cipher is a method or a mathematical algorithm used to apply encryption or decryption. It's pretty straightforward. And cryptanalysis is the study of, or analyzing ciphers in order to break them, or crypto systems. So for a secure cipher, you really need two properties. You need confusion, which is obscuring the relationship between the key and the ciphertext. Uh, Something called substitution does this. We'll go over that in the next slide. And then you need diffusion, which is obscuring the relationship between plain text and ciphertext. And transposition provides this. And we'll be going over that as well. So there's two primary types of ciphers, and those are substitution ciphers and transposition ciphers, sometimes referred to as permutation, but we're going to be using the term transposition because that's more common. Permutation is more used in as a mathematical term when you're dealing with more advanced crypto systems. So substitution is characters are being replaced. So you see hello there is being transformed into PAFFE. So the H is being replaced with a P, E is replaced with A, the L is replaced with F's, and the E is replaced with the O is replaced with an E. And transposition would be characters being rearranged. So hello is being scrambled into unreadable glob of letters, but the letters do not change themselves. So modern encryption systems are often described in three categories, defined by the amount of keys they have. This last bullet here, most crypto systems involve multiple operations of both substitution and transposition to provide diffusion and confusion. So a lot of the simpler ciphers will use either just transposition or there'll be a substitution cipher. But AES, for an example, which we'll briefly go over, uses both of those principles to be a secure algorithm. So starting with symmetric, symmetric encryption uses a single key or passphrase and a mathematical algorithm to encrypt data. Your Wi-Fi configured using a pre-shared key is an example of this. So you see it has one key. Asymmetric uses public-private key pairs to encrypt and decrypt. So you see two keys. And hashing is a unique set of characters, numbers, and symbols that represent a signature for an input, such as a password or file. And that's debatably zero keys, that would be. And we'll go over hashing in more detail as well, because that deserves its own explanation. So starting with symmetric encryption, which is more common than asymmetric, it uses the same key for both encryption and decryption. Key is often referred to as a session key in hybrid setups with asymmetric key exchange. So often you will have a key exchange that is asymmetric, and once that exchange happens, you will be provided with a session key that is asymmetric encryption. It's fast and strong compared to asymmetric, but the downfall is the secure key distribution is challenging. And here's some examples. And here's an illustration of the plaintext. Encrypt with a key, ciphertext, and then you decrypt with that same key to get the plaintext. Moving on. I provided this slide just to be just to have an example of a symmetric algorithm. This is AES, formerly known as Raindoll. It can have three configurations: 128-bit key, 192, and 256, defined by the number of rounds they have as well. And you'll see on the right here you have different phases or different rounds. You have byte sub, shift row, mixed column, and then you add your round key. So these the sub byte, for example, is substitution operation, and then shift rows is transposition. So you see how these work together to give us a secure algorithm. So that's really the takeaway here, is them being those principles being combined. Then you have asymmetric, which a lot of people have trouble wrapping their head around because you know, you have two different keys. Those keys are mathematically related, right? So I'll go through this bit on the left, and then we'll kind of walk through it. So it uses two different keys for encryption and decryption, often used to exchange symmetric keys. It's slow and weak. Private key must be protected. Public key must be shared. So and examples are RSA, Diffie-Hellman, ECC. So on our example over here, we have Bob and we have Alice. So Bob has a message. Hello, Alice. Bob is going to encrypt that with Alice's public key. So if it's encrypted with Alice's public key, it can only be decrypted with Alice's private key. So we're going to encrypt that, send that message along. Then Alice will take that message, use her private key that only she has, and decrypt it to hello, Alice. So that's that. But how is that possible? How is asymmetric encryption possible? This deserves a little extra explaining. Uh, we use something called intractable problems. These are problems that are easy to solve one way, but difficult to solve the other way. And difficult here means really only possible in theory. It's impossible with current computing resources. So in the future, you know, with quantum computing and such, these intractable problems would be less useful in encryption. Examples. These are kind of the main examples here. Factoring large integers into primes. It's okay if you don't really understand what this means. We're going to have an example on this first one here. Calculating elliptic curves in a finite field, so ECC uses that. Solving discrete algorithms, super polynomial, and exponentials. So those are kind of the intractable problems that are used in asymmetric encryption. And we'll go on to our example. So the example of an intractable problem on the last slide was factoring large integers into their primes. But we're going to work with smaller integers just to make it easy on ourselves. So a prime number is only divisible by 1 in itself. A factor is numbers you can multiply to get another number, right? So here we have a private key. The private key is the two factors, P23 and Q47. These are the factors of a prime number. Our public key is N. So P times Q is 1081. This is a prime number derived from the private key. So this public key is derived from our private key. And then we have an encryption key. We add this little encryption key. Then our message we're sending is 102. So we have an algorithm down here, or an equation rather. Our ciphertext is created by taking M raised to E mod N equals, and then so that's our equation. Then I wrote it out here. So that'd be our message 102, encryption key 17, mod our prime number 1081. Remember, our prime number is our public key, so everyone gets that. And then this is the message we're sending, the ciphertext 408. So let me go to the next slide, and we can kind of talk about what all this means. So this whole factoring large integers into primes relates to RSA, and here's the RFC, the request for comments, if you want to go read that. There's some good information there if you're a math nerd. Private and public key relationships are mathematically similar to factors and prime numbers. So the public key is mathematically similar to a prime number, where if you have the public key, you have the prime number, you're not going to necessarily know what the factors are. The factors are the private. So that's kind of how this is. It uses that principle. There's a lot more to it, but that's kind of boiled down what it is. You can derive a public key from a private key, but you cannot derive a private key from a public key. The only known method of finding the two prime factors of a large number is to check all possibilities one by one, which isn't computationally feasible. I hope that makes sense. On to hashing now. There's 5 attributes of hashing, sometimes 4, depending on what resource you're looking at, but I like these 5 here. So starting with the first one, deterministic, which means the same input will give the same output. So if you put the same input in to your hashing, and now we're talking about salts here, it's kind of out of the scope of this conversation, but if you're just using a saltless hash, the same input will give you the same output. And collision resistant, which means it is unlikely that different inputs will map to the same output. If different inputs give the same output, that is considered a collision, and we don't like that. Fixed size output. So the output will always be the same size no matter the input. So if you put hello, it's going to be the same as if you put multiple paragraphs. The output of the hash will be the same length, and we'll see an example on the next slide of that. They're one way, so they're easily computed, but you cannot reverse a hash. So from a hash, there's no way to get um, the plain text, outside of other methods that we're not discussing here. But just with the hash alone, you can't get the input. Um, Discontinuous. Similar inputs do not generate similar outputs. So if you change one little aspect of the input, the output should be completely different and relatively random. So moving on. So here's our hashing example. We have a hello is our input, and we have our two hashes down here, MD5 and SHA-1. So no matter what your input is here, you're going to have the same length output for these two hash types. So there's just two different types of hashes down here. And the common uses are to verify data integrity. So you can take a hash of a file, and then if you're worried about the file changing, you can take another hash of it and see if any content of the file changed. And then hashes are also used for authentication. So storing and transmitting plain text passwords would not be wise. So you can use hashes instead. So when you input a password on a system, your system then hashes that password and then sends that hash. In some implementations, this varies depending on the system or application. But and then the hash on the server side is compared to a database of password hashes, and they would see if they're the same or not. And some examples of hash formats are here, some different hashing algorithms. And there's a ton more found here. If you just want to search hashcat hash types, there's a ton. And then kind of it tells you what the salts are too. We're not going to talk about salting here because we're mostly focusing on cryptology. But yeah, that's there. So this is probably one of the more complex diagrams we'll be going over. This combines asymmetric asymmetric encryption with hashing. So we'll go over this diagram after we cover these points on the left here. Digital signatures combines asymmetric. I just went over that. Combines asymmetric encryption and hashing to provide non-repudiation and also integrity. Proves who sent the message and proves the message has not changed. So that's those two principles. And principle can be used for code signing. So you can this doesn't have to be a message you're sending. This could be a piece of software in a signature of the developer. So walking through this, you have Bob on the left and Alice on the right, and you have this message. So you're going to take this message, you're going to put it in a package. So that message goes in that package. But you're also going to take that message and you're going to hash it with your hashing algorithm, and you're going to get a hash. So then you take that hash that was output. Remember our example, we looked at the MD5 hash. It could be that, and then you're going to encrypt it with your private key. So encrypt or sign. These are kind of used interchangeably here. So you're going to take your private key, encrypt that. So only you can do that because only you have your private key, and that creates a signature. So you're going to put that signature in the package, and you're going to send Alice this message and the signature together. Alice, to verify that this message hasn't changed and that you sent it, she's going to take your public key. So Alice takes your public key and decrypts the hash that you sent. So that signature gets decrypted into the hash. Okay, she has that. She's also going to take the message up here. She's going to hash that message just like you did and take that hash and compare it with the hash she got from the signature. So hope that makes sense. There's the best example I could come up with simplified. And in this example, I didn't the original message isn't encrypted. I didn't want to add that complexity here. This is mostly about the integrity and non-repudiation aspects. Okay, so we talked about some more complex crypto systems. Now we're kind of going to go back to those two principles from earlier. Remember, we had substitution and transposition. So starting with substitution, which if you remember, it's characters being replaced, hence the name. Here's some examples here. We're going to go over a couple of them, but this is here for your reference. There's countless more. You could make your own substitution cipher if you wanted. It's not that complicated. So we're going to move on. Now here's kind of a go-to simple example. We have a rotation substitution cipher, sometimes called a shift cipher. Within that category, you have the Caesar cipher, which is also referred to ROT3, and you have ROT13. And these types of ciphers form groups. So multiple encryptions will cause a decryption. So ROT13 is rotating through the alphabet to 13 spots, and the English alphabet is 26 letters. So if you encrypt and then decrypt, you're going to end up back to the same spot. But ROT13, for example, or ROT3 rather, this example we have here, the cat we have for input, you would rotate 3 to F, A to D, and then T to W, and that's kind of your output would be this ciphertext FDW. So yeah, the ROT is always going to be just rotations through the alphabet. Now, arbitrary substitution, you're essentially mapping characters arbitrarily with replacements. So I have my input message might look like something like this on the top here, and then my output might be this. So you're just replacing like M with D, and so O with G, and so on. But if you look, so let's look at this. Let's look at this O here. So this O here goes to G, and then if we look at this O over here, that also turns to G. So you can do something called frequency analysis. If your input, the bigger the ciphertext you're analyzing, the easier frequency analysis is because your sample size is larger. So that's kind of a benefit. So you might instinctually think that it'll be easier if it's a short word, but that's not true. You would want as much ciphertext as you can get to make it easier on yourself. So here's an example of frequency analysis. There's tools that can automate this process. You can do it by trial and error if you like. You start by replacing most frequent letters, so whatever is the highest. So we have 54 T's in this ciphertext up here. So we're going to throw in an E because that's the most common letter in the English alphabet. So you're kind of going to do that. You're not going to have a ton of ciphertext, so there's going to be inconsistencies. It's not going to match up perfectly with the frequency. Do some spell checking, kind of like read along, say, oh, that's that letter. Like I said, there's online tools, and emphasis on the shorter samples being more difficult there. So to combat frequency analysis, there's something called a polyalphabetic substitution. It uses multiple alphabets to do multiple substitutions, and it resists frequency analysis. The most common example, there's a lot of different types of these, is I think it's pronounced veneer. Correct me if I'm wrong there. Uses a matrix of 26 alphabets. Uses a secret word as the key, and that secret word repeats to the plain text length. I'll go through this example in a second. Same plain text letter will translate differently depending on its character alignment. Identical letter pairs result in the same ciphertext letter, so that's kind of a downside there. So our plain text is hide this. Our secret word is tooth, but tooth will repeat, so it starts to repeat there, and it has to match the plain text length. And then we have our ciphertext. So how you do this is you take your H and you take your T from the secret word. So plain text is H, so you go up here, go to H, and then you go down to, see if your column's over here, H, and then you go down to column T, and then you have A, and then your ciphertext is A. So that's how this works. And you'll see we have a HT here. We also have one over here, so that's going to be an A. So, but you look at your, D O R, so D, then down to O R. Boom. So that's how you do that. And then you have symbolic substitution, which is really just different alphabets in pictorial form. You can try reverse image searching. You could try converting the symbols to alphabetic letters. Then you would have just arbitrary substitution, and then you could do the same techniques for that. They're usually monoalphabetic, so you don't have to worry about that sort of thing. This image is from Decode FR. If you want to go to this link and look at more of them. Here you have the Vatsiana cipher, I think it's pronounced. It's 26 letters organized into pairs. So it's a substitution cipher where you have concrete pairs. The key is those pairs there. So it's kind of like a arbitrary substitution, except you have a key. And there is auditory ciphers, the most common being Morse code. Morse code could be visual or audio, depending. So on screen here, I also have the link down below. This is Morse code, and there's a decoder, so you put an audio file in, or it'll pick up your mic as well. And here's the Morse code alphabet. I have a little audio sample. I'll play a bit of that. Last but not least, we have the one-time pad. It is one of the only unbreakable ciphers with a couple of stipulations. So it's comprised of two duplicate random keys that are created and given to each party that's communicating. Plain text, ciphertext, and key are all equal length. So you have a different substitution for every character on the plain text. It cannot be broken if the key is at least as long as the plain text, the key is truly random, the key is never reused, and the key is kept secret. So it's all around the key and the quality and the secrecy of that key. And here's an example here. So on the left, on the right. So that was substitution. Now we're moving on to transposition or permutation, as it's sometimes referred to as, and that's rearranging of characters. There's a few examples I provided there. There's less of these type of ciphers out there. So here we have the columnar transposition cipher. Its key length is the number of letters uh, in the key is equal to the number of columns. So columns are numbered in alphabetical order determined by a key. Repeated letters are numbered by appearance order. Plain text is added row by row, and then ciphertext is read by column in number order. So looking at our example, we have a key. Our key is apple. Our key length is 5. So our plain text is that pizza tastes good. So we're going to encrypt that into our ciphertext here. And how that's made is we have apple. So in alphabetical order, we have A, that's numbered as 1, and we have E is next after A, it's numbered as 2. And then we have two P's, so they're next. So we have L. L comes before P, number 3, and then our two P's, 4 and 5. So they're just in order there. And then our plain text is written in under that, row by row. That pizza tastes good. And then the ciphertext is generated by reading down. So TIAG, TIAG, and so on down the columns. So it's written row by row, read column by column, according to our rules. And that's it. And there's different alphabets, and your key lengths can change and all that, but the principles remain the same. Next, we have rail fence transposition cipher. The key is the number of rows or rails. So pretty simple rail key. Plain text characters are added in diagonal pattern. Ciphertext is read row by row. So we'll go through that. Also, you can, if you know what's a rail fence cipher, you can kind of brute force it by just upping the key every time, just checking if it makes sense. So our rail key is 5, standard alphabet. This pizza tastes bad is our plain text. So we're encrypting that. We get the ciphertext and our grid here. So we're going to write down diagonal, T, H, I, and notice the rail key is 5 here, so that's why we have 5 rows. And we're just doing up, diagonal, down, diagonal. And then you're going to read row by row. So that's why you have T, A, A, T, A, A, H, Z, T, B, D. And that's how the ciphertext is generated. And then we have a rail key of 3 over here, so it's 3. We have the same plain text, but we have different ciphertext because our rails are different. So that's that. So we're going to move on from ciphers, and we're going to kind of go into encoding, kind of the basics. So the encryption and encoding are kind of combined in a lot of cases, or used together. So that's why we're covering it together. So here's some definitions. Encoding to convert data into another format, often for efficiency purposes. Purpose isn't to hide a message, it's to make the data easier to work with from a software or a computing standpoint. Various other reasons, but it's really obfuscation at best, not really encryption. Character encoding, there's two main formats for that, ASCII and Unicode. Two primary standards for transcoding hex into characters. So characters being, it could be alphabetic letters or, punctuation and that sort of thing. Base, this is how a lot of encoding. This is how number systems are defined. They're defined by their base. So we're used to working with base 10 decimal. There's binary. That would be base 2, and so on. We'll go over that in a second. But other than that, we have base 16. That's hex. Base 32, base 64. Restricts the character set, often used to make data more readable by computers and software. Since characters are presented differently depending on the supported encoding standard, it is often easier and more reliable to work with hex. So when you're copying and pasting hex, it's going to paste into text. It's not going to paste into hex. So that's going to be important when you're looking at like a hex of a file or something. So just worth thinking about, keeping in mind. Just real quick, here's our two character encoding standards. ASCII, it's it's only Latin letters and numbers, so it's not used internationally except in certain situations. It's becoming less popular, but it still has its place. You have ASCII 7-bit and 8-bit, 128 and 256 characters respectively. Then Unicode, you'll see you have UTF 8, which matches ASCII's 8-bit. So the numbers, the bits. 16, see a lot more there, and 32. That's the reason these higher ones exist is a lot of it is for Asian languages or symbol-based, character-based languages. So that's why we have that. And here's an example of how encoding works with ASCII. So usually it's from hex. So 41 hex is character A. And you can look at any one of these if you like. 33 is 3, so that's a text ASCII 3. This is hex 33. So now number systems. This can be a little bit to wrap your head around, but number systems consist of symbols. Don't think of them as letters or characters. So jumping down to base 16, which is hexadecimal, you see A, B, C, D, E, F. Those aren't letters in this instance. They're symbols. They're part of the number system. So from the top, we have, and these are the most common you'll see, binary, zeros and ones, ternary, I think. I just learned this word. I thought it was a typo at first. Often known as trinary as well, is 120. Octal is 8, so you have 8 numbers. Base 10, that's what we're used to, decimal. Base 16, hexadecimal, you'll see a lot of that. Base 32, so that's the alphabet, and then 2, 3, 4, 5, 6, and 7. And then base 64 is numbers, capital and lowercase letters, and 2 additional symbols. And then I put a little link here. It's kind of neat. You can look at all the number systems. Go down that rabbit hole if you want. So now putting some things into practice here. Hex conversions. These will be some of the more common use cases for you. Hexadecimal is base 16, comprised of 16 symbols as we discussed. Keep track of which format your data is in. Yes, matters if it's text or not in a lot of scenarios. And here I put the hexadecimal binary conversions. So base 2 to 1, or that's not a 1. I mean the hexadecimal 1, right? And so on. So, and then you have the denary over here. And then CyberChef is on the right. You'll see a lot from CyberChef, and you'll be using it quite a bit if you haven't already. Hope you have. So from hex, so you always start with what your data's in. So if you don't put this from hex here, it's going to assume that it's text or ASCII or something. So do from hex to binary. So we have 2 A's, so we got 10, 10, or 1, 0, 1, 0. If we look at our chart here, if we go down to A, that's what we see here. So that conversion is correct. 8 byte length 8. And then down here, like I said, the hex number A converts to this binary. The A ASCII character converts to 41. So if you put just 2 hex, if you don't put this from here, do 2 hex, your A's are going to convert to 41 because it's taking these as ASCII. And if on the right here, you'll see A converts to 41 like we looked at earlier. So yeah, worth keeping in mind. So when you hear base, they're usually talking about base 32 or base 64, and those are padded with a equal sign. So to fill out the rest of the byte in those number systems. Padding is only required when the size of the data cannot be assumed in mostly network implementation. So they don't always even put, even if they should be padded, they don't always put it there. So But if you're trying to tell the difference, if you're looking at some data, you don't know if it's 32 or 64, you can look for these symbols, these two symbols here, the plus and the slash, or the numbers, like base 32 only goes to 7, so you can look for those. That's the thing, or trial and error. That always works. And here's the RFC. For so many things, you can just look at the RFC, especially with like networking protocols. Always look at the RFC if you're not familiar with the networking protocol. It's like a roadmap. You're really you're walking in the dark if you're not looking at the RFCs a lot of times. So might as well carry a flashlight. So XORing, it's a very common cryptographic operation to XOR data. It's called exclusive OR. So inputs on the left here. So the rules are outputs 0 if both inputs match, outputs 1 if both inputs don't match. So we have two 1s as the input. That will put 0 because they match. A 0 and a 1 are different, so they're 1. 1 and a 0 are different, so it's a 1. 0 and a 0 are the same, so it is 0. So pretty straightforward there. And this is in binary. It's always in binary. So here's a more complex XORing example that you may see. A little preliminary information. The character R, the letter character R in hex is 72. And this is the binary 0, 1, 1, 1, 0, 0, 1, 0. And this character isn't really named. This is just a Unicode character. It's in hex, it's 89, right? And then the binary is as follows. So on our first Cyber Chef recipe here, from hex 72 to binary is this. So that's our R there. Okay. From hex to binary 89 is this. And that's how we got that. So, and then we have the XORing. So you take R, the letter R, and so you can XOR. It does the translation for you. So XORing by 89. So you're taking the R as the input, and you're taking this. You're essentially XORing by this character, but we're not really concerned about that. We're more concerned about the actual value, which is 89. So we're inputting an R, which in hex would be 72. We're XORing it by 89. We're delineating that's hex, and the output is this U with a little hat, whatever that symbol above it is. So I wrote out the binary here for you. The R we talked about right here. This symbol here is here. So 0, 1, they are different. 1, different. 1, different. 1, different. 1, different. 1, zeros are the same. 0, different. 1, different. 1, different. 1. And we can confirm this. So we have the input XORed by 89, and then we're going to, so it's the same as over here. We got the U, and then we're going to put it into binary in here. So this U here is this binary, which by hand we can do this, and it's here. So pretty cool stuff. And you can work through this on your own or do your own examples too if you like. So this is a quick aside. It's not super related, but it's related to an example I want to go over. Magic bytes are file signatures. And here's a link if you want to go look at them. I provided a list here of common ones. You see a PDF, 25, 50, 44. So the hex is what we really worried about. This column's not very useful. Remember, you want to work in hex when you can, because it's more reliable when you're working in file viewers like this. So this is X or HXD. This is one of my favorite tools. So this is just a PDF I pulled up, and you can see this file signature. It's always the first couple bytes. It lines up with this PDF up here. So this is all known stuff. If you see a file you're not familiar with, you just look for a file signature, look it up, Control F, search it on a website like this, this Wikipedia page, and you can see exactly what type of file it is. So, because a lot of operating systems rely on file extensions, like Windows relies on file extensions, whereas some others will rely on this file signature to determine the file type and how to open it. So, yeah, worth knowing. So let's say we're given an unknown file. The first thing I would do with an unknown file, I would open it up and look at it. Look at the magic bytes up there, right? But this example, it looked weird. One of the reasons is it didn't have null. Uh, like this white space there would usually be a lot of like null space, which is like no zero in hex, so zero zero zeroed out. So since it looked weird and this file signature, I couldn't find anything on it. I put it into CyberChef and I did some entropy analysis because I wanted to see if it was compressed or encrypted. So entropy is the amount of randomness per bit. A truly random would be 1 bit of entropy. A 50% chance of a 1 and a 0 is true entropy. So compressed on this, they have the Shannon entropy scale here. There's a description down here if you like to look at that. But yeah, it wasn't at all random. It wasn't compressed. So compressed or encrypted would be way up here. It's even below. It's so unrandom. It's below English text. So it looks weird, but it's not compressed or encrypted. So it has to be some simple operation to unscramble this, right? So moving on to the next step. Okay, so as discussed, we have where the magic bytes are, the file signature should be right here. So we just have really, really random nothing that amounted to nothing when I searched it. And then I noticed these 89s, where the null space should be. So they should be zeros, just 89s repeated. So someone did an operation on this to give it that, and it probably messed up the file signature as well. So with that information, moving on. So I figured out that someone XORed this with a key of 89, hexadecimal 89. So XORing it with 89 again, if you XOR something twice, it'll return to its original form. So that's what I did. So you see here you have unreadable text, and then this file signature happens to come out to something readable. Not all of them do, but we at least see the null, all those nulls. We know that that's normal, and we see English words and things like that. This looks a lot more normal as far as a file goes. So pivoting to steganography, debatably, it's not really encryption. There can be you. It can have encryption, but it doesn't require it. So it's hiding a message, not scrambling it necessarily, but you could. A couple terms that you might see, LSB, at least significant bit. That's hiding a piece of the message in like the last bit of a byte that's not used, or as the name says, it's least significant. So an example would be like pixels in an image that would change the color ever so slightly, the human eye would not recognize. You would use those bits as to hold your message. And there's different programs that do this for you. It's not necessarily a manual process, but then you have DFT, discrete Fourier transform. It's mathematical transformation used to hide messages in media. So that's just another algorithm that's used. Often a matter of finding the right tool, find the one that is right for your file format. So look at the file format and see what tools support that. And does it take a password? Because some, like StegHide, takes a password, but you could also you could just leave the password blank as well. So if it requires a password, you might look at something like StegHide. And this is not an exhaustive list. I have 2 links here of more tools. And then in addition to these 2 tools, there's hundreds of steganography tools depending on file formats, because it could be audio, video, whatever. My favorite tool is Zsteg. So Zsteg, I think it's -A. So you can install this and look at the options, but it just runs. It's kind of the kitchen sink approach. It just runs a bunch of different checks on it to see what it's about. So StegHide takes JPEG, I believe, and Zsteg takes PNG and bitmap, I think. Could be wrong. If I remember right, that's correct. So one of these links, I forgot which one, kind of shows them by file format. So like WAV or MP3 and that sort of thing. So check those out. Then you have visual steganography. For this, you would need, so GIMP is free on Linux. If you have Photoshop, you can use that. Or you can use an online tool like I'm using in this photo. This is Forensically. So our image is up top here. And then we're doing what's called errors. We're doing error analysis to see alterations in the photo. And then I noticed, so you have to do it by eye if you're doing visual stego. So I looked at this image and I saw there's like, wow, what's that little bright spot over there? So I descaled the airs even more um, to make it super dark, and then I was able to see there was a flag in the image. So, and there's a magnifying tool on this tool as well. So, kind of how you do that. Audio stego can be tough sometimes. The first thing I always do is you open up the audio file over. So over here we have this is the audio file we were given, right? Looks normal. I think it's just beeps in this example. And then I put it. I open up the spectrogram, um, and then boom, there's our answer. So it's sometimes as easy as that. You just have to know where to look as far as uh, the analysis goes. Um, this one down here is a little tougher. The bottom one is the original, so it's a song, and then the top one was manipulated. And I believe this one was Morse code. Uh, so they used the decibels to kind of encode Morse code into the song. So to solve that, you could do it by hand, or you could flatten these out and play it back to the Morse code decoder. There's often multiple ways to solve every challenge, but yep. So yep, check waveform patterns. So the waveform patterns look weird like this. That might be something. Kind of gotta know what's normal in a lot of cases. So we went over a lot. There's a couple links there additional. Of course, there's more links on Canvas as well. But there's a lot to cryptology, and we barely scratched the surface in this. We didn't really get in deep into the math, um, but you're not expected to do that. You might have a couple RSA challenges, but that's probably as much math as they're going to throw at you. Um, yeah, let me know if you have any questions or anything about this. It took me a while to put these resources together, and kind of takes a while to be concise with this sort of thing. Try to not go too into the weeds on things. So thanks for listening, and have fun.